All right, today we're going to dive into one of the deepest, weirdest puzzles in all of quantum physics. Seriously. It's a rule that just seems to break all common sense. But what if the answer wasn't buried in some ridiculously complex math, but was hiding in a simple physical knot?
So here it is. This is the big mystery. You take an object, right? You turn it 360 degrees and, well, it's back where it started. Simple. Except for an electron, that's not true. A single 360-degree turn actually changes it into something different. To get back to its original self, it has to go around a second time, a full 720 degrees. I mean, how is that even possible? Now, the usual explanation for this involves some pretty mind-bending, abstract math. But a really fascinating model suggests we might be overthinking it. The solution, it turns out, could be something you can actually picture, something physical. It all comes down to topology, which is really just the math of shapes and knots. We're going to untangle a very, very special kind of knot. To get our heads around this quantum weirdness, we're going to start with something you can literally try at home. It's a famous physics demo called the Dirac belt trick, and it's the perfect real-world clue for what's happening at the tiniest scales of the universe. Okay, so picture this. You're holding a belt buckle with the belt hanging down. Now give that buckle one full 360-degree twist. You'll see the belt is totally tangled. It's stuck. There's no way to undo that twist without just twisting it back. But here's where the magic happens. Give it a second full 360-degree twist in the same direction. Now you can just loop the end of the belt over the buckle, and the whole twist just vanishes. The belt is perfectly straight again. So a 360-degree twist is permanent, but a 720-degree twist can be completely undone. Remember that. It's the key to this whole thing. So what on earth does a party trick with a belt have to do with an electron? This is where this new model comes into play. It asks us to imagine particles not as little dots, but as objects that are literally tethered or leashed to the fabric of reality itself. First things first. Imagine that an electron isn't just a point. Instead, think of it as a tiny, stable knot, a little twist that's actually part of the structure of space itself. It has a real physical shape, a form that lasts. And second, each of these little particle knots is connected to everything around it. Picture a flexible, flat ribbon. They call it a flux ribbon, that tethers the particle to some fixed background, kind of like an anchor. This ribbon is the particle's connection to the universe, just like the belt was connected to your hand.
So here's the absolute most important part of this idea. When that particle knot rotates in space, it's not just spinning by itself, it's physically twisting its own ribbon. The orientation of the particle is one-to-one with how twisted its ribbon is.
And just like that, with this simple picture in our heads, a little knotted particle on a ribbon leash, we can finally solve that 720-degree puzzle. It stops being some weird quantum mystery and becomes, well, just a matter of geometry. Think about it. When the particle rotates 360 degrees, it puts one full, stable twist into its ribbon. Just like the belt, that twist is topologically stuck. You can't get rid of it. The ribbon is now in a totally new state. But when it rotates another 360 degrees, it adds that second twist. And just like our belt trick, two twists can be maneuvered around the particle and smoothed out. Poof. The ribbon is back to its original, untwisted state. You know, this completely changes what spin even means. In this model, a particle's spin isn't about which direction it's rotating, it's about the physical state of its ribbon. Is the ribbon untwisted, or is it in that permanently twisted 360-degree state? That's it. Those are the two fundamental spin states we call up and down. And that explains everything so perfectly. A 360-degree turn doesn't bring the particle back to where it started. It flips it to the other spin state by putting that permanent twist in its ribbon. It's like flipping a light switch. To get back to the beginning, to flip the switch back, you have to rotate it another 360 degrees, creating the second twist that allows the whole 720-degree tangle to be undone. Now, solving the spin puzzle is incredible, but this model doesn't stop there. It also gives us a shockingly simple, geometric reason for another cornerstone of quantum mechanics, the Pauli exclusion principle. You know, the rule that says two identical particles, like two electrons, can't be in the exact same place at the same time. So let's picture the problem. We've got two identical electrons. In our model, that's two identical particle knots, and each one has its own tether, its own ribbon. What happens if we try to force them into the exact same spot with the exact same spin? Well, as you move these particles around each other, say you swap their positions, their ribbons are forced to braid. And this braiding isn't just a temporary tangle, it's a permanent topological change. Now, in standard quantum mechanics, this corresponds to a weird mathematical property, where when you swap two of these particles, their state gets multiplied by -1. This model says that weird math isn't just math, it's the real physical result of their tethers braiding around each other. And this quote from the source material really just nails it. That strange quantum rule, the one that says things turn negative when you swap them, it isn't just some random law we have to accept. In this model, it's an unavoidable consequence of the physical geometry of these ribbons tangling in space.
So here's the bottom line. For two electrons to be in the exact same state, their ribbons would literally have to be in the exact same place. But these ribbons are physical things. They can't just pass through each other. Forcing them into the same state would create an impossible knot. It's physically, topologically forbidden. And that is the Pauli exclusion principle. The reason matter takes up space is because its fundamental tethers can't.
Okay, let's just zoom out for a second. What does this elegant, beautiful, geometric picture really tell us about reality? It suggests something pretty profound, actually. So let's just quickly recap what we figured out. That totally bizarre 720-degree spin rule, it's just the physics of the belt trick applied to a particle's tether. Those two spin states, up and down, they're just the twisted and untwisted shapes of that tether. And the reason matter is solid and takes up space, it's because those tethers can't pass right through each other. The really huge idea here is that maybe the famous weirdness of quantum mechanics is just an illusion. Maybe these aren't strange, arbitrary rules that were baked into the universe at the beginning of time. Maybe they're just the natural results of a deeper, simpler, and way more beautiful geometric structure. Maybe the laws of physics are just the laws of knots.
And that leaves us with one last, really exciting thought. If spin and the exclusion principle can be explained by simple topology, what else can? What other deep mysteries of our universe aren't just abstract math, but are actually just knots, waiting for us to finally figure out how to untie them?